Okay, so in previous lecture, we discussed about Miller indices and interplanar spacing. Yes, so interplanar spacing is very important parameter to study the crystal. Okay, in the beginning we are just framing the map. Now we have come to a point where we can study the crystal. So for that, the most important law that commonly used is Bragg's law. Then only we'll go to the X-ray diffraction. Okay. So, Bragg's law is what? It was introduced by scientists W.H. Bragg and W.L. Bragg. They're actually father and son. That's how things work. Anyhow, this law, what it tells us, it gives a relation between wavelength, interplanar spacing. So, who is interplanar spacing? D. HKL. Sometimes it written as only D also, no problem. And then reflection angle. So it is not true completely. It is not only reflection angle. We should say this as glancing angle. Okay, rather than saying reflection angle, better to say this as glancing angle. So now glancing angle means what? See, we have taken here two planes. What kind of plane? This is crystal planes. How we are getting crystal planes? Because we are connecting lattice point. Just now this 6 circles I made, these are lattice points, and we get this plane number 1 and plane number 2 by connecting those lattice point. And there is gap between this plane 1 and plane 2. That gap is T. Now we are incidenting X-ray. Don't be misinformed like we are incidenting ray 1, ray 2 like that. We are actually incidenting a beam of X-ray. For simplicity of our derivation, we are saying that this is X-ray 1, this is X-ray 2. Okay, so X-ray 1 incidenting here, and it is getting reflected from the top of the lattice point. But X-ray 2, it is finding a gap between this point and this point, and they are entering inside and they are getting reflected from the second point. Now, multiple phenomenon like this will happen at a time. So we're just taking a simplistic case. Okay, so now these two rays will come out and they will interfere with each other. So we should have a basic knowledge of interference also. Interference happens between two waves which are coherent in nature, and this also we have to study more details. Unit 1, when wave optics, there we'll study more details about interference as well. So interference basically means combination of two or more coherent waves. What is coherent? Their wavelength must be same. Their phase difference, if at all, should be consistent all throughout. The frequency needs to be same. Since we are using a same X-ray beam, obviously these two are coherent in nature. They will interfere. Now interference can be two types. They can interfere constructively or they can interfere destructively. When constructive happens and when destructive happens, see, this is a crest of a wave. This is also crest of a wave. If you add them, obviously crest and crest will give you a longer crest and longer trough. In the other case, if one's crest is at the same time that the other, so this is up but this is down, so if you add them, you will get nil or very little amount of amplitude. So this is called constructive interference. This is called destructive interference. Okay, so constructive means when crest and crest come at a point. Destructive means when crest and trough come at a point. So ultimately the result which you are getting wave, its amplitude is high in constructive. In destructive, the amplitude of resultant wave is reduced or sometimes not at all there. So there is a condition when it will be constructive and when it will be destructive. The condition is that the path difference should be equals to n lambda. Now n can take value 1, 2, 3, all this. It is just numbers, okay, integers. So now lambda is what? Lambda is the wavelength of the wave you are using. That is your choice. You can take anything. So if this two wave has path difference n lambda, it will give you constructive interference. Ci, I am writing for constructive interference. Okay, if the path difference is 2n plus 1 lambda by 2, then this is destructive interference. Now destructive interference means it will cancel out each other. Two waves will cancel out each other. Now the thing with X-ray is not visible to human eyes. Like everyday sunlight we see, it's a white light. It's a combination of VIBGYOR, violet, indigo, blue, green, yellow, orange, red. These are visible to human eyes. But X-ray is not visible. Its wavelength is very, very small, that it is not visible to human eyes. So how to tell that destructive interference happened? It will not be dark. Constructive means bright, not like that. So constructive means their intensity will be high. We will use some indirect technique so that we know, okay, constructive interference has happened. Okay, destructive interference has happened. So there is no way of knowing destructive interference. There is a way of knowing constructive. Intensity will be high. We will use this X-ray to undergo some kind of chemical reaction so that we know, okay, constructive interference has happened. So that's why we deal basically on constructive interference condition. What is the condition? Path difference should be n lambda. Now what is this path difference? If you see ray 1 hitting on the top, going back, reflected. Ray 2, it has entered inside the crystal, then only it got reflected. So it has gone some extra distance. How much extra distance? AB plus BC. This things is parallel. They are going equal amount. Yeah. So what is the path difference between this ray 1 and ray 2? The path difference is, in this case, path difference is only AB plus BC. How much extra got? AB plus BC. Okay. So path difference is AB plus BC. Now let us find AB and BC. You see these two triangle AZB and BZC, they are congruent triangle. So AB and BC are equal. So AB plus BC equals to, you can write 2AB because both of them equal. Now if I find how to find AB, let us look into this triangle AZB. At Z we have theta. Who is this theta? Theta is glancing angle. Don't get confused with reflection angle and refracted angle, all those things. Okay, angle of reflection, let me remind, angle of incidence, this is angle of incidence. Yes, incident ray and normal, whatever is the angle, incident. This is angle of reflection. This is angle of refraction. But glancing angle means angle between incident ray and the plane. This is theta. So don't get confused between glancing angle and reflection angle. Glancing angle is angle between incident ray and the plane on which it is reflected. So this is theta. If this is theta, obviously this is also theta. Alternate interior angle. So if this is theta, sine theta will be how much? From here you can see Z at Z we have theta. This to this, Z to B is interplanar spacing D. So sine theta is here it is already written AB by, this is AB, this is perpendicular, by hypotenuse, that is opposite of 90 degree, that is D. AB by D. So AB equals to D sine theta. Then what will be AB plus BC? 2D sine theta, because AB, BC all equal, 2D sine theta. So what we are getting, n lambda equals to 2D sine theta. This is Bragg's law. Very simple one. N lambda equals to, why you are taking n lambda? N lambda is condition of constructive interference. Who is 2D sine theta? This is path difference between ray 1 and ray 2. Ray 2 is traveling less. Ray 1 is traveling less. Ray 2 is traveling more. How much more it is traveling? 2D sine theta. Either this difference is n lambda constructive, if not destructive. Okay. So this is called Bragg's law. We'll use this law to study X-ray diffraction. Now one most important question that is asked by curious minds, we say, why do you use X-ray to study crystals? Why can't you use normal visible light or UV, these things why we are not using? You see, how do we classify these electromagnetic waves? You see this figure here, we have gamma ray. Its wavelength is somewhere around 0.0001 nanometer. X-ray somewhere around 0.01 nanometer. Range is there, not fixed. Okay, so like 0.01 to 0.1. All these things are in terms of nanometer. These are X-ray only. Ultraviolet more than 10 nanometer. Visible is 400 nanometer to 700 nanometer. This is visible to human eyes. We are evolved to see that. Maybe other animals, cow, dog, they don't see all these colors. Okay, this is based purely on evolution. So next, this is infrared. This is also not visible. Its wavelength is higher, 1000 nanometer or more. Then radio waves. Their wavelength is further more. So you need to know that if wavelength is less, their energy is high. X-ray is highly energetic compared to visible or ultraviolet. Why? X-ray's wavelength is, this side wavelength is increasing, right? This side wavelength is decreasing. So wavelength decrease means energy increase. X-ray has high energy compared to UV and visible. Now someone might ask, if high energy is only required, why we are not using gamma ray? Why you are using X-ray? That condition we need to speak here now. You see, diffraction, we are saying we will study X-ray diffraction. Diffraction means bending of light around the corner of obstacle. Okay, so there needs to be some obstacle through which light will pass through and it will bend. See, if the gap between, this is the obstacle, like gap is there through this light wave is moving. If the gap is huge, why the light will bend? Light will go straight. If the gap is very, very small, then light will come back. Why it will has to bend and go through? When it will bend? Only when the wavelength and the size of the gap or the size of the obstacle is comparable. Okay, so if you are very thin and there is a door, you can easily pass through. Without bending, you will pass. If I become very fat and cannot pass through a door, I'll just come back. I will not try to pass through the door. If it is comparable to my size, then I'll try to pass through it by bending. So like not exactly same thing. I'm just giving an analogy to understand it better. So that is diffraction. Now X-ray wavelength is what I said, 0.01 nanometer to 0.1 nanometer. This X-ray wavelength and the gap between crystal plane are of comparable range. That's why we use X-ray to study crystal. Okay, what was interplanar spacing? We found in previous lecture, right? The gap between two crystal planes. Now when light tries to enter through these crystal planes, they undergo diffraction. So that is why we use X-ray diffraction. First, that is kind of a reason. We can use other also, neutron beam. Based on the material, we will choose what kind of beam we will use. So the X-ray diffraction is very important techniques to study crystals. And it is used in physics, chemistry, biology, complex biomolecules, everywhere. Okay, so and it's also a non-invasive technique. That is also the one important reason. Non-invasive means some ray will go inside and change the structure, change the position of atoms and molecules. That will be problematic for us. We don't want that. We just want to study as it is the crystal is. So that's why X-ray is used. It is non-invasive. It is not hampering the crystal. So that is our motivation. That's why we use X-ray. Now let us move. What are the parameters needed? What are the components needed for X-ray diffraction? First, we will need a X-ray source. In class 12, we have a syllabus detailed about how X-rays are created, produced. Okay, we're not going there. Then X-ray wavelength can vary. It can go from 0.01 nanometer to 0.1 nanometer. How much? 0.01 nanometer to 0.1. More also. Okay, so this is just a tentative range. You can say 0.1 angstrom to 1 angstrom. Right? It can go to 2 angstrom. This is just a subscale. So we need to control how much is the wavelength required for our material, for our system. So that controller is known as goniometer. And we need a sample holder. Whatever sample we are studying, we'll hold the sample somewhere. Then this sample, X-ray will hit the sample, incident on the sample. They will undergo diffraction. Now this X-ray is not visible. It is not like we see this X-ray, so okay, see there it X-ray are forming constructive interference. No. So we have to detect the radiation somehow. So that is another component. And lastly, we will need a signal processor and readout. We need to know how to study those X-ray which has been detected. So these are the basic components. Okay, X-ray source, controller of wavelength, a sample holder, radiation detector, and signal processor. We will see a typical XRD diagram here. So you see we have a X-ray tube here. From here X-ray is continuously coming out. We have a slit. Most of the time this slit is made up of lead. So we cannot use any random metal to go make the X-ray parallel, because X-ray penetrates through. X-ray is very powerful, very high energetic, though thus they penetrate different material. You need to use some heavy metal. It's like a heavy material, lead mostly used. Then this will go parallel. We'll have a crystal here. They will undergo both reflection as well as diffraction. Then we will use a photographic plate. Those who are undergoing constructive interference, their intensity of X-ray will be high. Those constructive interference X-ray of high intensity will form some spot on the photographic film. So we need to use some kind of film which will react with high intense X-ray and will give us a spot visible to humans. So that's how we will detect. So this is typically how XRD works. So now next go to what are the different techniques. This is basic. This is not how we study crystal. This is just theoretically. Okay. So next next lecture we'll discuss about Lawis method and powder method for X-ray diffraction.